Hey y'all, today we are going to start our second unit, which is logic, and we're going to start that by talking about inductive reasoning. So make sure you add inductive reasoning G.2.1 to your concept list. So inductive reasoning is basically observing patterns, and in the few examples we're going to do now, we're going to observe some patterns and see if we can continue those patterns based on our observations. So I have a sequence of 4 numbers here, and I want to find the next 2 terms in that sequence. So the terms are just basically going to be the next 2 numbers. So it looks like starting at 3, if I multiply 3 by 3, I get 9. And then if I multiply 9 by 3, I get 27. And then if I multiply 27 by 3, I get 81. So it looks like if I multiply each term by 3, I get the next term. So 81 times 3 gives me 243, and then 243 times 3 gives me 729. Shown another way, I have some shapes. I have a sequence of shapes, polygons to be exact. It's a 3-sided polygon, then a 4-sided polygon, then a 5-sided, then a 6-sided. So the next 2 terms are just going to go in that sequence: 3, 4, 5, 6, 7-sided polygon, and then an 8-sided polygon. So we just observe the pattern that's happening, and then we use that pattern to continue it. So I'd like you to try these 2. So I want you to press pause. I want you to give these 2 a shot on your own. Think them through. Find the next 2 terms in each sequence, and then press play, and I will go over the answers. So in the first one, it looks like if I take every term and I multiply it by 2, so 5 times 2 is 10, 10 times 2 is 20, 20 times 2 is 40, 40 times 2 is 80, times 2 again gives you 160. So these are the next 2 terms in the sequence. The next one's a little trickier. The first number doesn't start out with a denominator, so we'll divide it by 1. So now it might be a little easier to see that if I multiply the denominator by 2, I get the next denominator. So 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and 16 times 2 is 32. In every case, the numerator stays 1. So after we observe a pattern, we might be able to make a conjecture, which is really just drawing a conclusion based on inductive reasoning or based on the pattern that we observe. So here I have a pattern of shapes and colors, and I want to know the color of the 15th shape. So rather than draw the shapes and color them in until I get 15, I could observe this pattern and then I can make a conjecture, which means I can draw a conclusion about what the color of the 15th shape will be. So I have purple, maroon, green, purple, maroon, green, purple. So it looks like the 3rd shape is green, the 6th shape is green, so every 3rd shape will be green. That means that my 9th shape will be green, my 12th shape will be green, and then my 15th shape will also be green. So again, I only have 7 pictures or 7 shapes colored in, but I can make a conjecture based on this pattern about the 15th shape without drawing them. Down here, if I want to make a conjecture about the sum of 2 odd numbers, so sum means to add, so I want to know what the result is going to be when I add any 2 odd numbers. So I can add a few odd numbers and see what I get. So 3 plus 5 gives me 8. 11 plus 9 gives me 20. 21 plus 3 gives me 24. So it seems like every time I add 2 odd numbers, my sum is even. So my conjecture is going to be that the sum is even. So give these 2 a try. I want you to make a conjecture about each of these scenarios. Remember that sum means to add, and product means to multiply. So pause the video, give these 2 a shot, press play, and check your answers. So here I want to sum or add an even and an odd number, something like 3 and 6. If I add 3 and 6, I get 9. If I add 11 and 8, I get 19. If I add 22 and 5, I get 27. So it seems like whenever I add an even and an odd, I get an odd number, so the sum will be odd. So just by running through a few examples, I can make a conjecture that the sum of an even and an odd number will always be odd. Now it's good to point out that this doesn't necessarily mean that this is true. I'm just making a conjecture. I'm making a conclusion based on a pattern. The product of two odd numbers, so let's multiply some odd numbers. So 3 times 5 is 15. 9 times 5 is 45. 3 times 9 is 27. So it sounds like the product of two odd numbers is also going to be odd. So I mentioned quickly that not always are the patterns going to, or the conjectures are not always going to be completely correct. You're just drawing a conclusion based on a pattern you observed. So if I can provide one example that shows that a conjecture is incorrect, then it's called a counterexample, and that means that my conjecture is not always true. It might be true sometimes, but not always. So let's find a counterexample that shows this conjecture is false. I have two angles, angle 1 and angle 2, and I'm saying they're supplementary, which means they add to 180 degrees. So this statement says that if they're supplementary, then one of their angles is acute. So one of their angles is less than 90. So can we think of two angles that are supplementary where one of them is not acute? And the example is if they're both 90 degrees. If they're both right angles, they're supplementary, but neither of them is acute. So we would call this a counterexample. The sum of two numbers is greater than either number. So I can add 3 and 5 and get 8. Okay, great. That's greater than both 3 and 5. But let's think of one way that that's not true. If I add 0 and 1, the sum is 1. 1 is not greater than 1. So this is a counterexample. So I want you to give these two a shot. Again, pause the video. Try these two on your own. Think about it for a minute or so. See if you can provide a counterexample for these two conjectures, and then press play, and we'll go over the answers. So this conjecture says that the product of two positive numbers is greater than either number. So product means to multiply, and so if I multiply two numbers, 1 and 2, two positive numbers, my product is 2, and 2 is definitely bigger than 1, but it's not bigger than the original 2. So there's a counterexample. Here the difference, that means to subtract. I should have said that before I had you pause, but I think you know that. The difference of two integers is less than either integer. So if I subtract two integers, this conjecture is saying that the result will be less than both of them. So I'm going to subtract 2 minus 1, and I'm going to get 1. So 1 is less than 2. It's less than that 1, but it's not less than the original 1 that we started with. So this is a counterexample. So both of these conjectures are true at some point, but I have found counterexamples for both of them, so they're not always true. So if you look in the description section below this video, I've provided a link for you. I want you to click that link, and it should take you to a Microsoft form. You're going to need your school login, and you're going to log in there. You're going to answer 2 questions on that form. You're going to hit submit, and then you're going to show me your notes.